So as we can see the question on the screen, so there is a rod okay of 10 mm diameter. So this will be the diameter, we'll write as 10 mm. Okay, it means it's a circular cross section, and length is 200 millimeter is the total length of the bar. Has a nodal displacement due to axial loads. Okay, there will be having two axial displacement for this, that is given as u1 is 1.2 millimeter, whereas u2 2.8 millimeter is the nodal displacement at each node. The position of the rod as shown in the figure. Okay, so position means the exact location or the coordinates for the x-axis and y-axis. The position, what is the exact position of the rod which will be given in the question. So the figure will be like this, given figure, and here the positions are given as first x1 here as 60 millimeter, and where x2 as 260 millimeter, and at the mid having one point here. Okay, that point denoted as q, and that x value for the point is 150 millimeter. So actually these x1, x2, x are the exact position of the rod. So now you need to find the displacement at point Q. So what will be the displacement at point Q? It means you have to find out displacement at Q, and also find the stress, the strain energy for the rod, and take E value as Young's modulus for the given material is 210 gigapascal. Okay, so this is the exact condition of the problem. Now first let me explain what is x1, x2 and x. So for example, if you have taken some reference from here in x and y, like this, a reference line for the rod, then from here if you take this as u and this as x line, okay, x will be the horizontal line. So from this reference to this node having a distance of x1, this will be x1, and from the same reference to this point q, that is x, this will be the x1, and with the same reference to this x2, that will be x2. Okay, so from the reference it is taken as x1, x2 and x. Okay, so it's been given the values like u1 is 1.2 millimeter, and where u2 is 2.8 millimeter, and if you say this is L is 200, there is a length for the element, and Young's modulus is given as 200. First, before that, diameter is 10 millimeter. Okay, and Young's modulus, E value is 210 gigapascal. Okay, so one thing we observed here, many of the values are in millimeter, like the displacement, length, diameter, and here we can convert this Young's modulus also in terms of millimeter. So 210 into 10 power of 3, again it will become megapascal. So 210 into 10 power of 3, where 1 megapascal is equal to Newton per millimeter square. Right, hope you understood the converting the values. Now once you understand this given value, because always we have to maintain everything in a one single format, like same units, whether you can go for meter or you can go for millimeter or centimeter, everything should be in the standard format or standard units. Now we will go for calculating the displacement at Q. Okay, the solution we can go for now. Right, just so what will be the solution here? As we know that for a rod the displacement is linear, okay, because along the axis there will be displacement, and for rod the displacement equation will be U x is equal to n1 u1 plus n2 u2. Okay, and where n1 and n2 are the shape functions at node 1 and node 2, and we can write n1 as it is x2 minus x by L, and where n2 is equal to again x minus x1 by L. Now you can substitute the value of x2, that is 260 minus x value is here already it's mentioned 150 by length is 200, and similarly we'll make for n2, x value is 150 and x1 value is 60, it's 60 by length is 200. Now you just make in calculator, it's 260 minus 150 by 200, got 0.5. okay, here n1 is 0.5 and where n2 we will calculate 150 minus 60 by 200, that is 0.45 is n2, is n1. Okay, now we need to calculate the displacement at point Q. Okay, we'll write as UQ to understand that UQ, point Q, displacement will be U. Okay, so the equation where n1 into u1, n1 is just we calculated as n1 0.55, and here is u1, u1 value is 1.2 which is given in the question, plus n2 is 0.45 and u2 value is 2.8, this is also given in the question. So now if you make these two, 0.55 into 1.2 plus 0.45 into 2.8, so got 1.92 millimeter, because it's a displacement U at point Q. So there is a displacement at the node Q is 1.92 millimeter as per the condition. So, right, so this is a very important task to complete this. Later we can go for calculating the we have to calculate the strain, element strain. This is the second one. So here just is a formula where strain epsilon is equal to, it's u2 minus u1 by L. Just substitute these two, you are getting the strain, that is u2 minus u1 by L. u2 is you know as 2.8 minus u1 is 1.2 divided by 200. So approximately we are getting here 0.008. Right, that is the strain. There will be no unit here. Next, again similarly we can calculate for a stress, that is sigma is equal to E into epsilon. So you know the value of E and epsilon. Epsilon just now calculated, just make into that 210 into 10 power of 3 into epsilon value is 0.008. Now make it this 210 into 10 power of 3 into 0.008. So got as 1680. 1680. So stress, the unit will be Newton per millimeter square. Right, now again we can calculate the strain energy. Just I will write the formula, you just substitute in this case. Okay, so what is the formula to calculate the strain energy? That is U is equal to, it is caps U 1 by 2 K U2 minus U1 close the bracket, or where K is the definition for stiffness, that is we can write as in place of K A E by L in place of K. K is the stiffness formula for K, that is again U2 minus U1. Okay, so now you can you have a question, what is A? A is equal to what? It is the area, cross section area, a circular pad, it is pi by 4, again D square here. So what is the value of D? That is given as 10 millimeter. D is equal to that, you substitute here, then you are getting A in millimeter square. Again smallest we are having and length is also given, and again U2 U1 from here we can just substitute and you are getting the strain energy. Okay, so thank you for watching, have a good day.